so nice to relax in the mellow Parisian weather after that brutal 33:45 final. Math has made me weary. Mathematicians say. We? Ha ha ha! Do you know who I am? No. What? But you took 33:45, yes? Oh, are you Bezout? The guy with the lemma that doesn't even make any sense? Who has a really sparse Wikipedia page reducing you to a basic caricature of a French person? Wait, no, that is a great lemma. It has a Wikipedia page too. But I don't even know what it means. Well, then I can explain it. Oh, it's fine. J'insiste. No, really. So do you know what my lemma, my masterpiece says? Honestly, no. It is the greatest common divisor of any integers, at least one of which is non-zero, can be written as the smallest positive linear combination of the two integers. Why does one have to be non-zero? Any linear combination of zeros is zero. Are you saying that a GCD could be zero? Did you even take 33:45? Well, I guess zero doesn't divide anything. Well, I guess you are right. Okay, that's good and all, but the proof doesn't make any sense. What does not make sense? We will show that the smallest linear combination divides the greatest common divisor, and that the greatest common divisor divides the smallest linear combination, so they must be the same. Well, when you put it like that, it makes more sense. First, we must show that a linear combination as such even has a positive minimum. I mean, of course it does. There's a minimum positive integer in the first place. Excellent intuition. Perhaps there's a spark of mathematical aptitude in you. Merci. What you say is the principe de bien commander? What? The well-ordering principle. It states that any subset of the natural numbers has a minimum. I guess the set of positive linear combinations is a subset of the natural numbers, now that you pointed out. Indeed, so it must be positive. It is bounded below by 1. Yes? But is it empty? I don't think so. Let me set it up. Choose two integers, a and b, to find the linear combination of. Then let d. Let d equals as plus bt, where s and t are integers. Well, let s equal a and t equal b for this case. Then you're going to have d equals a squared plus b squared. So d is a positive integer and the set is an empty. So it's bounded and not empty. We can apply WAP now, right? Now since we have WAP, let's say that d is the smallest linear combination of a and b. So now we can go on to the meat of the proof. It's a little bit easier to show that the GCD of a and b divides d. Do you remember the division algorithm? Of course I do. Well, alright, use it to write a and b in terms of some common divisor, L. Alright. There exists integers, let's say k sub 1 and k sub 2, such that a equals k sub 1 times L and b equals k sub 2 sub L. Oh, and then let d equals k sub 1 times L plus k sub 2 sub L. Wait, so it equals the quantity of k plus 1 times k plus 2 times L. So any common divisor divides any linear combination, so the GCD must too. So how big must d be? I don't know, we just showed divisibility there, right? Well, if a non-zero number, m, is divisible by another n, it tells us that m is greater than or equal to n. Oh, so d is at least as big as the greatest common divisor of a and b. Exactamente. So does that finish the proof, I guess, since the GCD divides b? No, did you listen to me before? We must now prove that d divides both a and b. Oh, well, I guess if d divides a, then a equals dq, and no, tu ne sais pas. We need to show it. All we can say is that there exist integers q and r such that a equals q times d plus r. That is all divisibility algorithm tells us. Oh, and with r greater than equal to 0 and r is less than d, right? So this is using the division algorithm. Yes, exactly. So how can we show that d divides a? Well, I guess in the algorithm, r needs to equal 0. Yes, so since a equals q times d plus r equals a minus q times d, which also equals a minus q times the quantity as plus bt. Remember, d is a linear combination of a and b, so it can be replaced with a times s plus b times t. And you can factor this and move this around to find that r equals 1 minus qs times a plus negative t times b. Then we have that r is a linear combination of a and b. Okay, this contradicts everything. We assumed d was the smallest positive linear combination and that r was positive. So r doesn't exist? Remember what we were looking for? Oh, r must be 0. And d divides a. And by a similar argument, d divides b. And if the GCD divides d and d divides the GCD, so the GCD is the smallest linear combination of A and B. Magnifique. Okay, so now can you explain the Chinese remainder theorem? Au revoir!